So thank you everyone for coming. Thank you to the organisers for the invitation. I'm just going to give a quick overview of some of the ideas that I'm going to try and explore in this talk. So one is that I'm going to ask when can agents rationally disagree? So I'm very interested in agents' rational behaviour. And I sort of get a bit impatient with theories of human or animal behaviour that rely on the idea of agents having this sort of taxonomy of cognitive biases and irrationalities without some explanation of where those come from. So clearly people do disagree about a lot of things, and I'd like to know, when is that a reasonable thing for agents to do? And hopefully as a consequence of that, I want to explore why we as a society seem to be so polarized, so why we disagree so much, especially in sort of our political and social discourse. Why do we seem to be ever more likely to enter into rapid and strong disagreements with people? Most of the explanations I've seen for this, as I'm going to describe in a minute, seem to be based on very irrational use of information by people. And as I say, that sort of makes me somewhat unsatisfied to just leave it there. And then, based on that, I want to ask, is there any sort of rational way we can understand the sort of dynamics of, especially online social media type discourse that we see? Because as the learned Mr. Bravo on the side here suggests, I think we can all agree that discourse on places like Twitter is a bit of a bin fire, and I'd like to know, why does that originate? Is there some sort of reasonable basis in our behavior that could lead to the sort of ways that we behave? And in approaching this, I'm inspired by sort of the work of Robert Aumann from the 70s in this famous paper. I just wanted to get a show of hands. Who has either read this or at least is aware of the agreement theorem? Okay, about maybe approaching half of people. So if you are not aware of this, I'll describe it in a second, but I would strongly advise you to go and read this original paper. It's only 3 pages long. On the very first paragraph, Aumann suggests that what he's about to do is completely trivial, and then he goes on to prove a result which has its own Wikipedia page. So it seems to me something that's worth your time to go and have a look at. But what Aumann does in his paper is he proves this theorem which says that essentially rational agents cannot agree to disagree. So about a matter of fact, if I say, for example, based on the information I have, I think it's got a 50% chance of raining tomorrow, and someone else says, no, I think it's 30% chance, then if that conflict is based on the fact we have different information, the very fact that we disagree is new information to each of us. And by sort of continually thinking about the fact that the other person still doesn't agree with us, we should keep changing our beliefs until eventually we do agree. So a sort of perpetual refusal to agree, or an agreement to disagree, should not be possible when it comes to matter of facts. And this is reflected in many of the common models of opinion dynamics that we have. So if we think, for example, about the group learning, which is a very common model for how opinions spread on a network, you might have a focal agent here who takes some sort of weighted average of the opinions of their neighbor and adjusts their own opinion accordingly. And except in the cases of very special sort of network dynamics, what this tends to do is lead you towards consensus. So if you iterate this for long enough, everyone ends up with the same opinion. Now that's clearly not what happens on something like Twitter. We do not all end up thinking the same thing about every opinion that we could have. So people have noted the existence of polarization in particular and looked in depth at various mechanisms that could induce that. And one, for example, is a sort of homophilic interaction where you tend to strengthen your connections to those who you already agree with, weaken connections to those you disagree with, and as a result, you essentially split the network into 2, each of which agrees with itself, but which don't have to agree with each other. But this is extremely odd from an informational perspective. So why would I go to all this effort to listen to people I know I already agree with? Like, now, if I think to my sort of usual day job where I'm thinking more about animals, an animal should be searching for new information in the world, not information that simply tells it what it already thinks. So why would humans do something different? And I think the root of a lot of these problems is that we get, to some degree, confused between 2 potential sources of conflict in the world, between people's opinions and what they express about what they want or what they think. So you can have informational conflicts where individuals disagree about potentially a matter of pure fact based on the fact that they have different information. So I may think it's going to rain today, you may think it's not. We're trying to decide whether we should take an umbrella. But that conflict is based on the fact that we might have different information. We've seen different weather forecasts. One of us did or didn't watch the weather forecast this morning. Whereas differences in preferences are often conflated with this, but are quite different. So if we're trying to choose a restaurant, we may very reasonably differ about which restaurant we want to go to, not because we've read different reviews, but simply because we have different food preferences. So if I'm a vegetarian, I'm not necessarily going to want to go to a restaurant that everyone else thinks is great on the basis that they're probably thinking that's great because there are well-known meals there that they want to have, but they're mostly meat meals. So as I say, these are often conflated and confused, particularly in more heuristic models where the tendency to sort of follow what others do can be reflected in something like a social force or just a heuristic sort of copying rule that doesn't speak to the sort of conflict that it's trying to resolve. But these different conflicts should have very different resolutions. So I'm going to try and sort of unpack a bit of this with a very simple model in which agents may have different preferences, definitely get different information, and try to sort of see how they resolve that. So we'll start off with a model in which agents are trying to guess which of two options is the right one for them. So they're presented with a very simple world. There are two options, A and B. For every agent, there is a reward of some unit value on one side, no reward on the other. And their only goal is to try and guess which side has the reward for them. And notably, whichever side is the right one for me might not be where the reward for another player is. Each player will get a piece of sort of imperfect information privately about which of these options is best. So they'll get something that's a signal Z, which is drawn from a normal distribution with mean 1 if A is the correct option for them, with mean -1 if B is the correct option, and with some adjustable parameter here, epsilon, which indicates how reliable that private information is. So if epsilon is very high, it means these signals are not all that informative about what the right option is. And conversely, if epsilon is low, you can imagine these distributions sort of shrink and they would almost perfectly indicate which option you should choose. And then the fun comes in when they try and actually make use of what they see each other doing as well. So I might get a piece of information that tells me something about the world, but then I see someone else's choice as well, and I try and integrate what I've seen privately and what I've now seen socially as well. So let's walk through an example. Imagine that we've got two agents, and agent 1 initially chooses option A. So this immediately implies something about their private information. They would only choose option A if their private signal had been greater than 0 in this case. So something that indicated A more than it indicated B. Now we ask, what does agent 2 necessarily believe, if they're rational, about what their best option, x2, is? So not about x1, which is how z1 was generated, but about x2. So we can use Bayes' rule and just update based on all the different bits of information we have. So we're asking, what's the probability here that for agent 2 that its reward lies in option A, given the signal it's got z2 and this sort of censored information it has about what agent 1 saw. And we can sort of plug through each of these. I think I've got them highlighted for each term. So we've got a likelihood ratio here about the private signal. And conveniently, if these are normally distributed, we can simplify that down to a nice exponential term. But this is the easy bit. This is, I got some signal and I work out what it means for me. But then we've also got this social signal as well. And note the different indices here. So I'm asking what the probability is that z1 would have been greater than 0 if x2 is -1 or if x2 is 1. And from that we get these sort of ugly terms here. And I have to introduce a new probability alpha, which is the probability that my best option is the same as your best option. So alpha here is a probability of between 0 and 1, and we can relate it to a correlation which is between -1 and 1 between our preferences. We get these sort of ugly terms here, which are all cumulative normal distributions. So these are basically, this is taking the guess, what if they had a different preference to me? What if they have the same preference? And then the same in reverse in the denominator. And I don't plan to belabor the mathematics too much, but if we do a lot of rearranging of this, what we can basically say is that agent 2 will choose B now, as long as their private signal is less than this sort of combined ugly term here. And what we've got is things to do with alpha, but also things to do with the environmental noise epsilon. And if we were doing like a one-shot game, that's where we'd leave it. But now, if we allow the agents to try and change their mind and resolve this conflict, then this provides new information. If agent 2 chooses B, it provides new information to A. So we now know, if agent 2 has chosen B, that its private information must be less than this threshold. So agent 1 can now choose whether it thinks it wants to update its choice, and it will do. So let's call that term I had before T2. It will now update its decision or not based on whether its private information is more or less than this new threshold here. So before it chose if Z1 was more than 0, but now it's got a new threshold, T1, based on what it knows about the threshold of agent 2, which is T2. And as you'll probably be able to see, you can go back and forward with this, constantly updating T2 in the light of T1 and T1 in the light of T2 and back and forward. And if you do that, you get sort of long-term equilibrium values of these thresholds for different values of rho, so the correlation, and different values of epsilon. So you can see especially for different values of epsilon, you get different large-scale differences in the critical values in absolute terms, but you see the general same pattern, that the stronger your rho is, the wider these intervals become. So let's say this is T1, this is T2, or the other way around, because it doesn't matter, they get to some sort of symmetry. If I've got a low correlation, these thresholds will eventually equilibrate at very small values. Okay, we can perpetually disagree as long as our private signals lie outside of those bounds. So if we've got a low correlation, it's quite easy for us to disagree. I need to have a signal up here, you need to have a signal down here. But if we have a high correlation, then I need to have a signal all the way up here, and you need to have a signal all the way down there, or vice versa. So clearly we're going to agree more, as you would expect if we're more correlated. But exactly where those thresholds are will also depend on what we think about the environmental noise as well. And notice that none of the correlations here are 1. So what happens if we put a correlation of 1 in? Well, this is the same plot as was on the right-hand side before. You see these have all balanced out, but if I have a correlation of 1, these just go on rising indefinitely. I haven't proved that, but it's fairly clear that it will do. If someone wants to help me prove it, I'd be very grateful. And so eventually these thresholds will meet any private information I have. So this again sort of confirms Aumann's point that rational disagreement isn't possible if we have perfectly aligned preferences, or equivalently if we're talking about matters of fact. But based on those critical values that we do eventually get, we can ask, well, what's the probability we will eventually agree for any given correlation and any given environmental noise? And if we do that for various different assumed correlations and assumed noise, we get different sort of calibration curves. So if the noise is very low, so 0.1 or 0.5 here, we essentially get a completely straight line. So what that's telling us is the probability we will eventually agree is completely linear with rho. And the reason for that is we will essentially agree if, on this occasion, we actually do share the best same side. So we get private information that's good enough, we just follow our private information. Social information has almost no effect. But when we get to higher noises, social information becomes useful because our private signals are sufficiently unreliable that it's worth paying attention to what other people do. And so you see these bends up in the curves up here, showing that I'm still going to agree almost all the time with someone, even if our correlation is only, say, 0.8. So you get much stronger sort of social force when the when the noise is higher, and we can get strong social forces even when the correlation is not 1. And for anywhere on this calibration curve, we can sort of ask, well, how much should we be agreeing? And therefore we can invert that and say, we agree in the right amount given the correlation that we assume we have. So I'm going to propose a two-stage model where agents, instead of sort of being told from on high how much they tend to agree with each other, actually try and learn that as part of their decision-making process. So everything that I've developed so far is sort of based on the idea that agents know what epsilon is, they know what rho is, they know everything about the world except whether A or B is the best choice for them. But in reality, of course, that's not the way that we operate. We meet someone new, we don't know if we share preferences with them. We don't know how much we're going to agree about decisions typically, and it's something we have to pick up along with actually using the social information they provide. So I'll have a simple model where decisions are made according to the model I just described, but then there'll also be a learning stage where agents try to update their beliefs, especially about their correlation rho, based on whether or not they've been agreeing a lot or not in the past. So to get specific about that sort of learning algorithm, what they'll do is make decisions, and from those decisions, they'll sort of count how often they agreed or disagreed in the past, and from that, they'll make an inference about what their general probability of agreement is. And they'll try and match that to their expectations from the calibration curve. So if they've inferred that they agree 80% of the time, and they, for some reason, think epsilon is 10, then they'll infer that their rho should be probably about 0.4. So in this formula down here, I've got a couple of regularizing parameters, A and B as well. These are sort of necessarily there because if A and B disappeared, then the first time I agree, I'll think I always agree. So that would be a problem. So we can have these regularizing parameters, and this is essentially like placing a prior distribution on our rate of agreement. So if A and B are 1, which is what I'll use most of the time, that's like saying I have a uniform prior between 0 and 1 on agreement. And therefore, an implicit prior, as we'll see a bit later on correlation as well. So this whole thing just sort of goes back and forward. They update this, they have a new rho, they make a new decision, they update this again. You could do it with different stages, so you could have more or less decisions between each update. I don't think it would make a vast difference, but that's something we could discuss. So I'm going to go through a number of case studies of sort of what happens for different values of the model parameters. So first, I'll consider a world in which private information is very reliable. So here, these are fairly arbitrarily chosen, but epsilon here is 0.5, and I'm introducing eta. So epsilon from now on will represent what the agent thinks the environmental noise is. Eta will represent what the environmental noise actually is, and here they're the same. And in all of these examples for the moment, I'm going to be imagining there's a real correlation between the agents, which is 0.7. So here, this is very good private information. If an agent makes a decision by itself, it will be right 98% of the time. And so, as we saw, they have this sort of linear calibration curve that tells them how often they ought to agree for different correlations. But what they'll actually find is they agree nearly 80% of the time for almost any assumed rho. So if they're down here, assuming that their rho is 0, they'll get a strong push to push them upwards. If they're here, they'll get a push backwards, and so they'll end up at this sort of stable state here, which conveniently enough is at 0.7. And so if we actually simulate that, we get over like thousands of agents, and each pair of agents gets 1,000 decisions. You'll find that they tend to cluster very tightly around 0.7, as we'd expect. So that's all good. But it should be noted, they're doing a really good job here of inferring what rho is, but they don't really need to, because they've got great private information, so they don't really care what the other person does anyway. So it's sort of like, it's a waste of their time. They can do something brilliantly, but then they can just ignore it anyway. If we actually raise the noise, and I wrote here high noise, and then I realized as I looked at it this morning that this noise actually isn't that high, because here the agents are still making the right decision nearly 70% of the time by themselves. But you see these curves, you have the same pattern that the red curve is above the black. There's a push towards a stable point, but the push is now much, much weaker. So these two curves are coming very close together. So in theory, there'll be a stable point here, but in practice, when we simulate it, we get this quite wide distribution of where they end up, sort of stably deciding whether they agree or not. So even in a reasonably sort of low noise world, the agents are finding it very difficult to infer what their true correlation is. And if we really do ramp up the noise, so here they're only 54% accurate by themselves, then the calibration curve and the actual curve of how often they agree have basically completely coincided. So now they're finding it completely impossible. And you see that there's this wide number of different values of rho that they eventually settle on. So this is clearly a problem, because this is where they would like to make use of social information, but they can't make use of social information if they have no idea how much they agree. But the situation can get worse. All those cases were cases where they did at least know how noisy the world is. So they know how reliable their private information is. But that's something we can obviously change. And we might imagine in humans that's something that could quite radically change. We might become adapted to one way of thinking, and suddenly we're presented with this new media where things operate differently, or we're subject to sort of propaganda that might change how we think. So a simple thing we could do is say, well, what if we think our private information is really good, but we make it noisier? And what happens there is our stable point, even has now moved far away from 0.7 and actually moves roughly to 0. So it seems to us that we have no correlation at all. So essentially, because the information is now much more random than we think it is, we end up disagreeing far more often. So we basically agree half the time, and so we think we have no correlation at all. And that's what the agents do. They eventually cluster around correlation of 0. So just by making the world noisier and sort of not either informing the agents or not letting them adapt to that, they can believe they share nothing in common with each other, even though they are in fact very strongly correlated. But things can get worse still, because it's much more interesting if we go the other way and we make the world cleaner than what the agents are expecting. Or conversely, and probably more realistically, we change the agents' expectations to make them think the world is less knowable than it really is. So imagine we have a reasonably low environmental noise of 2. So if the agents understood that, they would be right about 70% of the time. But we've somehow convinced the agents that the world is noisier than it really is. Well, now the relationship between the red and black curves here is inverted. So what was a stable point in the middle has become unstable. And the agents will now fly up to either 1 or down to -1, depending mostly on what the first few decisions that they make are. And in this case, the situation isn't completely catastrophic. They go to 1 more often than they go to -1. I mean, they're making a mistake here, but perhaps it's not a bad mistake if they think they're more aligned than they really are. But we're starting to see this sort of catastrophe that's going to happen, that agents become convinced that some agents become convinced that they're completely misaligned, even though they basically share the majority of their preferences in common. And if we take that further, so we basically bump up all those noises a bit more, we can essentially make this as symmetric as we want. So here we've convinced the agents that the world is highly unknowable. The world is reasonably noisy, but we've convinced them it's highly unknowable. And now it's basically a coin toss which way they go. And so whichever the first few 1 or 2 to 3 decisions they make will completely determine whether they decide that they're fully aligned or fully anti-aligned. And you get this completely polarized distribution. So you can imagine if you played out this at scale, you would end up with a network in which every connection is just 1 or -1. And so you see a clear potential source here for polarization, for toxic discourse, and for the emergence of a sort of an idea that there might be these sort of 2 armed camps. Like when you meet someone, they're either going to be completely aligned with you, and if you find out they're not completely aligned with you, well, the only other alternative is they're completely the opposite to you. So everything I've shown so far was based on the idea that I introduced those regularization parameters earlier, and so far I've been using A and B is equal to 1 throughout. So this is the case that I've been looking at so far. But that doesn't necessarily have to be the prior that we use. Right? So that would suggest that somehow I know nothing about what the correlation might be between me and someone else before I meet them. So it's basically just because it's mathematically easier to place the prior on the agreement rate. These are the implicit priors over rho, which is why they look a bit sort of uglier. This isn't completely uniform. It's got these sort of tails. But basically, if I think that the agreement rate could be anywhere between 0 and 1, it suggests a prior over the correlation, which looks reasonably uniform as well. But I can try out these other priors as well. So if I make these numbers very small, it suggests that we either agree 0% of the time or 1% or 100% of the time in most cases. And I can also try out priors that basically say, well, we'll probably agree most of the time. And if the noise is reasonably low, so here this is agents getting decisions right about 84% of the time if they were just left to their own devices, then these agents are quite capable of learning what the true correlation is to a reasonable degree of accuracy, apart from maybe in this case over here. So if I make the prior extremely targeted towards rows of -1 and 1, then many of the agents sort of get it right and go to 0.7, but we get these sort of outliers where some go to 1 and a tiny proportion go to -1. But more or less, if the world is full of really good private information, then the agents will be able to learn how much they agree. But recall, that's exactly the case where it doesn't matter. So here, if you're able to make the right decision yourself, say 84% of the time, maybe if you made absolutely optimal use of the other person's information, that might go to like 87, 88. So it's not like a life-changing amount of information. Things look very different in our unknowable world. So in our world where private information only indicates with, say, 55% reliability which of the two options is better, then we have, again, the same sort of priors here. But now, if we look at what happens to the agents in the simulation, they just conform more or less to what the priors tell them they should do. So everything becomes completely self-fulfilling. So where we have a more or less sort of uniform prior across the correlations, this is the result we saw earlier, that the agents converge to somewhere between 1 and -1, but who knows where it's going to be. If we go to something more extreme, we can essentially convince them a priori that everyone is either completely with them or completely opposed to them, and their expectations will be confirmed. So they'll initially either agree or disagree, and then rapidly converge to seeing exactly that. So after, say, 3 or 4 sort of more or less reasonable discussions, they'll end up, every discussion they get the same answer, or every discussion they get opposite answers. And the only way we can get them anywhere near the right answer reliably is to give them a prior that happens to be centered on the right answer. So if we somehow convince them that the world is full of people who more or less agree with them, perhaps imperfectly, but are generally aligned to where they are, then that's exactly what they produce as well. So this is to some degree showing us the power of a narrative about what our world is like, that people will often shape what they believe about how much people agree with them, how much information they can get from others, based on what they expect and what they've heard social relationships might be like. So I've got a couple of more slides of conclusions on this, and then perhaps some very early stage suggestions. And I should have noted right at the start, this is all exceptionally new and probably not entirely thought through, so I very much welcome some feedback. Yeah.
Could I just ask about the noise term? Because you could imagine that some individuals are more experienced in the environment, therefore their noise is actually objectively less than, say, my noise if I was inexperienced. And you may then expect to have some individuals being more reliable in terms of social copying. Have you looked at that, like asymmetry of noise?
No, I mean, it's, I think the general intuition, so I mean, if we take a step back from this model in particular and just ask, like, if I know that you've got better information than me, then I think your intuition is completely correct that I should pay more attention to what you do if your noise is lower than mine.
I was thinking, like, maybe older individuals could be more influential because you assume that perhaps they're more experienced, or perhaps animals making decisions, biased decisions depending on perceived age or something.
So if you've got some sort of credible external signal that says I'm more informed, so as I say, age, or perhaps like some signal of fitness, like size.
Or confidence. Someone that appears confident, you might assume that they know more, even though they don't.
Yeah. So I think in general, if you imagine that someone has better information than you, you're absolutely right that you should follow them more. It's certainly not something I've looked at in the context of this, and I think one of the things I would like to look at is, because everything so far has been sort of symmetric, but I'd like to look at a world. For example, one thing I want to look at is, what if only one agent is sort of confused? What if one agent knows the world that they live in, the other one is sort of confused? Is it sufficient to just have one confused agent to get these pathologies? Or can one agent who knows more fix the problem? And similarly, like, yeah, could I either infer something about what the other agent's noise is, or if you say, like, you've got some sort of external signal, what if my noise is like 10, but I know yours is 5? Then do the dynamics play out differently, both in terms of like how the conflict is resolved, but then also potentially in terms of how much I learn about our correlation as well. I think there's one just behind you.
It's more of a clarification. So are you thinking of this as dyadic interactions or many individual interactions? Is that part of you?
Well, so the model is completely dyadic. I think, yeah, I mean, an important extension would be to say, well, how does that play out when you start placing lots of people together? Potentially, like, not just doing relentless interactions with each other, but I interact there and then I interact here, and would it play out differently, or could it be decomposed into just?
And that is where probably Ian's comment of hierarchy of information and the degree of confidence you have in now.
Also, complex contagion, you would need to have triads, like, you know, because this would be simple contagion, wouldn't it?
Well, this is, I mean, because this is dyadic, it doesn't make any difference. But certainly, if you were having, let's say, triads, I mean, what the previous work I've done on this would suggest is that, you know, what matters is, like, yeah, two agents doing something is quite different to one. I mean, especially when you get a number of, if it's a well-connected network, the order in which that happens can be extremely important as well.
Sorry, so back to your thing, Ian. I mean, it's the relationship between epsilon and eta, right? So experience may actually be detrimental if the world changes.
Yeah.
Right. So if you have a very strongly affirmed epsilon, the eta shifts.
Yeah.
Right. So we shouldn't trust old people in that case.
Yeah,
Never trust anyone over 30.
Yeah, I mean, the few of you in the room who might have read one of my previous papers know I love to play this game where I basically tell agents that the world is one way and then I make it a different way. But I think especially in human behavior, that's extremely important because, you know, I mean, I'm old enough. I grew up in a world, you know, without a smartphone, without the internet initially. You know, each of us has got like some stage where we grew up without this, and then we had that. And each of these new communication technologies takes time to get used to, like, what is information like in this environment. But we're all doing it together, right? So if we're all doing it together, we could get these sort of like, we can end up in pathological equilibriums as we attempt to work out whether or not, you know, this is a reliable source of information. Was that 10 minutes?
It was actually, no, it was a question, actually.
Okay, yeah.
And I suspect it's the same as Ian's question and a couple of the other questions, but it's kind of more in the kind of narrower mathematical sense, right? You began with Aumann's theorem, and in some sense it seems like the criticism is the criticism of the hypothesis in the theorem. Like, how on earth can one assume that two rational agents have the same priors? I think that's the, I mean, one can kind of make that assumption specific to kind of different contexts, but like, how does one justify the hypothesis that
two agents have the same it's not so much a different prior. So Aumann says, and I tend to agree with this, that if agents have different priors, the most parsimonious reason they have different priors is that they have different information that leads to the different priors. So if you go back far enough, they should have the same prior.
But development biologists would kind of disagree with that, right? Like as you just put it with the phones, each of us is growing up in different ways, and we are kind of seeing.
Yeah, well, I guess Aumann would say that. I mean, our different upbringings and our different experience in life is the information we bring to the table that develops our prior. So when I'm learning about our disagreement, I'm also learning about our different experience. But what Aumann didn't look at, I mean, through no fault of his own, I mean, he was interested in, can we just disagree about a matter of, like, truth? But he wasn't investigating what we want to do in the world or what we want to get out of the world. So that's why I said it's so important to think about preferences. So, like, we cannot necessarily just agree about what the best restaurant is, because there's no objective like this is the best restaurant. There's the best restaurant for certain types of people who want certain things. And that's true of most of our sort of political and social discourse. There are better societies for me, there are better societies for you. Those don't necessarily align.
Thanks.
Yeah.
So, isn't the value of this raw or like correlation between the preferences or the eta, the noise and the signal, aren't all these numbers matters of fact, or the the distributions of these numbers?
Well, if we look at something, so here, what I'm assuming is this is a matter of fact. So there's a real sort of correlation between what we want. So, I have certain tastes in food, you have certain tastes in food. We could argue about where those tastes come from, but at any given time, that's a matter of fact that we share a certain degree of taste. This is a matter of fact. This is, how noisy signals really are in the world. Again, it could be transient. It's something that could change over time, but at some given instant, the signals I'm receiving came from with some degree of noise. And this is, it's a matter of fact, but it's in my head. This is what I think. This is how bad I think signals are. So this and this can be different. And this potentially is something that I can be misled about if it's different from this. And these rows here, these rows are generally, I'm talking like these are inferred rows, so these are not matters of fact. This is what the agent's guess row is, but the actual row is where the red line is.
Yes, so what you have shown is that the agents could converge to completely wrong value of raw,
Yeah.
but the value of raw is a matter of fact. So
Yeah.
the agents would get the matter of fact wrong.
I see what you're saying. Yes, because here it's not about whether the agents agree on what row is. So the agents are just wrong about, you can make a wrong inference about the world. And I can make a wrong inference about the world. But if we're able to share what we infer, we can't disagree about what we infer from the same information. Yeah. James?
Just going back to Ian's comment, so we actually did some work on confidence weighting in opinion sharing in this scenario on graphs. And in the synchronous case, so using signal detection theory like you're using, it's nice because you can actually do the graph dynamics analysis, and you can actually, under some plausible assumptions about like naive Bayesian agents exchanging views and confidence weighted views, you can actually get information cascades and negative information spreading. And then you can rescue it by going to an asynchronous case where you have drift diffusion models, which we've seen in previous talks here, because their earlier decision makers tend to have better quality information than the drift diffusion model if there's uncertainty about how good their signal is. So,
what about the role of sort of uninformed? When we previously looked at uninformed and informed individuals, you can have very strongly opinionated minority that can dominate, but then if you have a portion of uninformed individuals, actually they return control to the majority, they democratize the process.
I'm not sure we systematically varied that, but yeah, it would fit into the formalism.
Okay. I think I'll just finish my last couple of slides and hopefully we'll have some more time for discussion. We saw that, priors can make a big difference as well. So a few conclusions and some very early suggestions. So it seems within this model, although I've failed over many weeks now to try and prove it conclusively, but it does seem that, this conforms to the general concept that Aumann put forward, that rational agents should not agree to disagree on matters of fact. And I'm very confident that result is true. Even though here because the difference between Aumann's paper is that there the agents basically share their posterior beliefs. Here they only share like a censored version, which is why the proof would have to be slightly different. But it's fairly obvious that agents can and should reasonably differ when matters of preference are at stake. So there is absolutely no reason that we should eat in the same place, even if we've got all the same information, just because we're allowed to have difference of preference. So I think that speaks to an idea that we should be, when we've seen examples both of experimental data and observational data. We do this in animals and we do it in humans, but we should think more carefully about when we see conflicts and how they're resolved or not resolved, whether these conflicts are informational or about preferences. And I think, as I said at the start, these are often conflated and then not thought about again. Because most models just sort of say, well, this is the rule by which you update. It doesn't really specify why that's the rule. So it doesn't really get down to the nitty-gritty about whether that's because you're trying to share information or you're trying to deal with the fact that you want different things. We saw that how much social information actually weighs on you and how useful it can be. is determined by sort of intuitively how correlated your preferences are. So if somebody is not correlated with your preferences at all, they can't give you any useful social information. But also environmental noise is very important. So when you've got brilliant information yourself, then even slight differences in preferences mean that somebody else's actions are of no relevance to you because you've got this brilliant information. Like I usually give the example of like when I'm at the train station, if the board is working, it doesn't matter if hundreds of people are running off to the train because I can just check if my train is ready to go or not. But if the board suddenly isn't working and hundreds of people pile over to the platform, I'll probably go and have a look and see if that's my train that's supposed to be going. Changes to the environment that mean the environment changes relative to our expectations, or equivalently, things that change what our expectations are, even if the environment stays the same, can cause agents to misjudge how much they have in common. So we might think about the sort of Adam Curtis sort of idea about how Vladimir Putin runs Russia, where he tries to make the world very unknowable. He makes it seem like the truth cannot be found. Different people say different things about what should be matters of simple fact, and people lose faith in the idea that they can know what is true. In our own societies, we see the growth, for example, of like conspiracy theories and the idea that the world is run by secret elites, meaning that we can't get access to the truth. And that sort of narrative can mean that we misjudge how much we have in common with other people. And we saw with the priors that belief in the belief in the existence of polarization can be completely self-fulfilling. In what are probably the more realistic forms of this model, where agents don't get really good private information themselves, or at least the more interesting forms of the model. So what suggestions does this suggest? Well, we can, to some degree, counter this problem of thinking that we hate each other by trying to establish an early sense of rapport with people. So what we know is that in those cases where people fly off to 1 or -1, it's based on the first few decisions. So when we have early interactions with people, if we can find areas of common preference, of common ground, such that our first few interactions are positive, it suggests that we might converge to the sort of, even if it's a misguided, perhaps the less problematic misguided equilibrium. We can create a counter-narrative to polarization. So, polarization is quite a strongly established empirical fact of discourse. It's certainly something we should investigate and report on. But there are, of course, many things on which we generally agree with each other, and we should be more vocal about that sort of thing. So a lot of people have tried to create these campaigns about more in common than divides us, where we seek for those aspects of our experience where we clearly share common preferences. And that can be something that we don't usually see, because I guess if we all agree on something, it becomes a bit like the air that we move in. We just don't notice it very much. So trying to stress to people the number of things that they agree on can persuade them that the world is not composed of essentially good guys and bad guys. And we can try to persuade people that the truth actually is knowable. Especially in our own societies where it is reasonably easy to get good information about things if you want. We can push back against narratives of conspiracy theories and against this idea that the world is only knowable if you're inducted into some sort of secret society. And hopefully that can, again, push people away from this idea that the world is simply composed of those in your camp and those in the other camp. And I think that's my last slide, so I'll leave it there. Hopefully we might have some more questions as well. Thank you.